Okay, I think we're being recorded here. So, welcome to Lecture 3, Electronics 2. So, today we're going to talk about differential amplifiers. And this is a very important topic, in my opinion. It needs a lot of attention, not just because it's part of the course, but I think it has a lot of major applications in the real world. And it's a very, very famous circuit that a lot of people use or a lot of companies use. And it's most definitely an interview question because it involves a lot of technicalities. And of course, when you're learning during your lecture, it won't be mentioned to you like that, but it's a very important topic because a lot of times interview questions come from those types of circuits that actually serve a purpose. So now you might be wondering, why am I not covering current mirrors? Well, that is way too easy for me to cover here. Like, if you don't understand current mirrors, like, I don't know what to tell you. Like, this is so simple. You got a transistor, you have a certain current. You Given the schematic of a circuit, the current is going to be repeated. There's nothing deeper than that. But if you guys want me to do one, just put in the comments if you want a current mirror video. I'll do it. But in my opinion, it's too simple. So we're just gonna go right away to do. We're just gonna go right into differential amplifiers. Now, I want to motivate the need of a differential amplifier. Now, in electronics 1, we learn how to find the gain of a circuit, V out over V in. That's how you find your gain. However, in the real world, your gain, when you have an input voltage, it's the input voltage plus some noise. Now, I'll give you some time to reflect. I want you to think about where exactly most of that noise is coming from because you're working with a circuit. So think about it for a minute. All right, now that you've thought about it, you could pause the video, think about it. Most of that noise actually comes from the 60 hertz frequency. If you remember from rectifier circuits, or in Canada, generally all of our plugs, all of the things that we receive in our houses from the plugs are all 100, just 60 hertz, right? Frequency. So that's the noise you're gonna have in your circuits because there's so many wires, like in your ceilings, wherever you work. It's all that 60 hertz frequency. Okay, so that's gonna create a noise. It's gonna create a small voltage added to your input, and if your input is your input voltage plus a small amount of noise, your output voltage would also have your output voltage plus that noise. That noise is still there, and in some applications you need such precise measurements that you cannot afford to have that noise. This is why we have derived this differential amplifier. This is why people came up with the differential amplifier, is to get rid of that noise. And when you go to class, you learn how to solve circuits. It's very easy for that point to fly right over your head and you don't know why the hell you're learning about differential amplifiers. But differential amplifier is very, very important if you want to minimize the noise very, very efficiently and precisely in your circuit. So this is what we'll do. Now, you might look at the circuit and be like, holy hell, it looks like a spider. No, yeah, it kind of looks like that, but again, you gotta chill and then look at it piece by piece. It's not too hard to understand. So what I want you to look at this first is look at it overall. Okay, it looks like any other circuit. Here you have VDD, that's your DC power supply. You have a current source here, and throughout the course of electronics 2, maybe your actual lectures, you probably realize that most current sources are actually transistors, right? You use transistors to create your own current source. It doesn't exist, right? You can't go to the market and buy a current source, right? You have to make it yourself. So there's that. Now, what I want you to also realize is, if you look at this schematic here, if you look at this situation, you have um, transistors just like the previous lecture, like the cascode amplifier, right? You can see that you have transistors cascoded right here, okay? And then you can see that the same input is being fed into this similar circuit right here, where you also have a cascode. So you see, you're already seeing how we have a differential amplifier. However, it depends on the concept we learned in the previous lecture, right? So everything is going to build up in that sense. We're learning new ways to solve these circuits. And you can also notice that we have dark circles here, which means DC, DC, DC. This is AC. And you will also notice that on this side, we have AC input. So first key point, you have to realize that we have two inputs to your circuit. We have one input here, and we have the other input here. And you will also realize that V out is right here. V out is just not a point voltage. V out is a differential voltage. It's between this point and this point. So this would be V out 1, and this would be V out 2. So it's the voltage difference between these 2 points. Now, why do we have two input voltages and then two output voltages? To tell you in words is to get rid of the noise. Now, you might believe me, you might not believe me. However, I will show you the proof for that. Okay, I will show you the proof. And it's very important to understand proof sometimes. I get it. It can be annoying when you're asked to do a proof on an exam. However, you can't really escape proofs. And it like one of my closest friends really told me that back in the days, like when you understand a proof, it really builds an intuition and you never really forget the foundational knowledge, right? So, Josue, if you're watching this is for you right now, okay? So I'm gonna prove it live. So like I said before, you have V input one, and this is equal to some input voltage plus the n. Here in this case, the n is the noise. Now, everything that I'm writing here is a function of time. So you have the input voltage function of time, all right? Even the noise is a function of time, right? It's a random noise, right? It's a function of time. Okay. And then we also have V input 2, which is equal to V input. Actually, it's going to be equal to minus V input plus Vn. Why minus? Because you have two input voltages right here. You got an input voltage right here. You got an input voltage right here. However, that minus sign does not mean that this is plus 2 volts, this is negative 2 volts. Yes, you can kind of interpret it this way. However, I want you to think that this and this one, the V in 2 is 180 degrees phase shift from V input 1. Does that make sense? So it's 180 degrees phase shifted. Just just like the gain of common emitter, I think it's minus GM or out, right? So then minus just indicates that 180 degrees phase shift. Same situation here. But in magnitude, the input is the same, right? So if this one is 1 volt, this one is 1 volt, it's just 180 degrees phase shifted. Okay? And as such, we have our output voltage. So V out 1 would be equal to V output plus Vn. What is Vn? It's the noise, right? The noise on the input is still going to exist at the output naturally. And we have V output 2. This is equal to V output plus V minus V output. Why? Because of the 180 degrees phase shift again, plus Vn. Now you might be saying, why do I have only the V input 180 degree phase shifted and not the noise? Well, the input I'm giving into the circuit, I'm choosing, I'm saying, hey, this one is the same, but the other one, V into, is going to be 180 degrees phase shift of the first one. I'm doing this by choice. I'm choosing to do that. Why? Because this is the best way I can do it. The noise, I have no choice over that. It's whatever wires I have in the building I'm working with. So I don't have control over that. So I can just put it as noise. So I have plus noise, right? Or minus noise. However, since we chose plus, we have to be consistent every time we add the noise, right? So our math is correct. So you could say minus noise, like for sure, that's up to you. But I chose plus because I don't like to deal with minus signs. I always make a mistake. So now, if you were looking at a traditional circuit, so I'm just going to write here traditional amplifier. What would your gain be? The gain would be V out over V in, right? So AV. Let's choose V output 1 and V input 1, just for instance. So we have V output 1 over V input 1. What is V output 1? It's V out plus Vn, the noise. And V input 1 is V in plus the noise. So you look at that. The noise is in the gain, right? The gain is composed of the noise. We do not want that. We want a gain to be a gain, right? We don't want the noise in there. So I'm just gonna highlight this in red to say, hey, this is a big no-no. We do not want this, right? If we use a traditional amplifier, we have this kind of situation. Differential amplifier, as you can see, we have two nodes, and the output is taken. The output not itself is not a node voltage with respect to ground. It's the difference between V output 1 and V output 2. So here I have our differential gain, AD for differential gain. So this is going to be V out 2 minus V out 1 over V in 2 minus V input 1. Okay, now I just need to replace with the things that I have. Now, what is V out 2? It's minus V out plus Vn plus the noise minus V output 1, which is V out plus Vn. Okay, and V input 2 is minus V input plus the noise minus V input 1, which is V in plus the noise. Now I can keep on going further. So I expand the numerator All right, I bring in the minus sign, plus Vn minus V input minus the noise. Now, here's the important part. If you look over here, and change colors, the noise cancels out. So you don't have the noise in your circuit anymore, right? You don't have the noise in your circuit. Now you have minus V output, so then minus V2 V output, and then minus V input, that's minus 2 V input. So then these would cancel out. And what is V out over V in, guys? That's your regular gain. That's a V. So you can see that using a differential amplifier, that noise disappears completely. So I want you to really look at this for a second, pause the video, kind of go through it again in your own head, and make sure that you understand everything coming here, and make sure you safeguard that in your memory here so that you understand that this is the point of the differential amplifier. Do that while I sip some tea. Now, this what I did here was a proof to give you intuition behind the differential amplifier. However, we still need to calculate the gain of that amplifier. And to calculate the gain of the amplifier, we're going to have to apply new circuit strategies that can help us with that. And what we're going to figure out today is something called circuit splitting. If you look at the circuit here, it looks very symmetric. Now you might say that, yeah, of course. Like if an artist looks at this and you probably say that this is not symmetric, but electrically it is symmetric. Why? Because this voltage here is the same as this voltage here. Our symmetry is only in terms of voltages and currents. So this voltage here is the same as the voltage here. Same thing, same thing. This you have an input, this you have an input. All right, it's in magnitude, these inputs are the same. All right, these sources, they share the same current source going to ground. So that's another part of symmetry here. And also you have VDD, where these two transistors are drawing DC power supply, right? You're getting the power from the DC power supply there. Okay, so you can see that this circuit is symmetric, right? I can kind of do this, and you would believe that this is electrically symmetric. Now we want to do our AC analysis. So what we're going to do, we're going to ground all of the DC. So this is ground, ground, and ground, right? So this is going to be grounded, 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 grounded. Now what I want you to pay attention to is this point. When you have symmetry in your circuit, right? When you have symmetry in your circuit and you have a current source attached to ground, this point you can consider it to be virtual ground. I'm not going to prove this because, first of all, I don't know how to. It's just something. We never learn how to prove it because I think it's beyond the scope of even undergrad. But you can kind of see that the way you can kind of visualize it is when this voltage is high, this voltage is low. Why? Because these two voltage sources are 180 degrees phase shifted. So this being high and this being low constantly cancels each other out, causing this to be ground. Does that make sense? You see what I mean? When this voltage is increasing, V in 1 is increasing, due to the 180 degree phase shift, V input 2 is decreasing, right? But in magnitude, they're the same. Now, this voltage here means that this is increasing and this one is decreasing. And because they're symmetrically increasing and decreasing, it causes this point to be virtually ground. Only in AC, not in DC, right? Only in AC. But since we're calculating gain, we're AC analysis, so that means we can consider this to be virtual ground. So I'm going to call this point P virtual ground. Now, if you look at the circuit, you can see that, hey, it looks very similar to the one we solved earlier in the previous lecture. Now, once you have virtual ground here, one thing you can do is you can split that circuit symmetrically in two, right? And you get rid of this completely. You find the gain of the circuit that's remaining, and that's going to be your differential gain, right? You solve the circuit, only half the circuit, you have your differential gain. Now, a lot of people make the mistake. They solve the circuit, they find the gain of the circuit, and they multiply it by 2 because they say, hey, we have two sides to the circuit. That is wrong, right? You don't multiply by 2. You just find it for this circuit, and that's your gain. That's it. You don't need to multiply by 2. I'm not going to prove why I don't need to multiply by 2, but if you come over here, you will see intuitively these two cancel out. You don't need to multiply by 2 because you'd be multiplying your gain by 2. These two naturally canceled out. So just understand it from here, right? So number one, virtual ground. You notice your virtual ground. you notice your electrical symmetry in your circuit. Once you have your virtual ground and you understood the concept of the virtual ground, you can split your circuit in two. Now, you might say, I ignored this one and then analyze this one. You're absolutely correct, okay? But here, I'm going to split the circuit in two, ignore this part, and I'll calculate the gain of this one, all right? And this gain is going to be my differential gain without multiplying by 2. I don't need to do that. Okay. Now, what is the gain equation? Minus GM R out. So gain equals minus GM R out. Now, I'm not going to show you how to calculate GM. GM is going to be equal to GM1 using the bro code. I never calculate my GMs. If you do not know what the bro code is, go watch lecture 2. I'll explain it in there. All right. This saves you probably like 10-15 minutes on a final exam. So go learn it. Okay. This is how you calculate GM, bro code. Now, how do we calculate R out? Again, we talked about that in the first lecture, so you can go refresh your memory. In the second lecture, we learned on how to calculate gain, but in the third lecture, we're applying again for differential amplifiers. So if you look over here, you would see that we're left with this circuit, okay? Now we have a PMOS network here, and then we have an NMOS network here, okay? So that means I can replace this one, this one, this one, this one with resistors. Why? Because they're all grounded everywhere. I'm going to start by replacing M7. So I'm looking at the gate source. I'm looking at the drain, all right? RM7 will be the resistance here. And I want to replace this transistor by a resistor. So I'm looking at the drain of a PMOS. So I go to my circuit here. I'll try to find a PMOS. Okay, there we go. This is the PMOS. I'm looking at the drain. This is ground and ground. So it's just going to be RO. In my case, since this is 7, it's going to be RO7. All right? RO7. Okay. Now, ROP. ROP, why ROP? ROPMOS, because it's all the PMOS network. So this has been replaced by a resistor. Now I'm looking at the drain of this one, but this source is connected to this resistor that we have up here. So we need to do that now. Okay, so here's the situation here. We got it. We're looking at, crap, where's my laser? We're looking at the drain. This is grounded and this is connected to RS. In our case, you might see RS here. This RS with RO7 because we replaced this MOSFET with a resistor, all right, from the previous substitution. So now ROP is going to be equal to this equation, GM RO RS. So it's going to be in our case, it's MOSFET 5, so it's going to be GM5 RO5, and RS is this one, RO7. So GM5 RO5 RO7. Now you might say, you might want to use this, you can use this. I always use the approximated because it's made my equation easier and saves me time because I don't have to write. Okay, so now we have ROP. Everything here has been replaced by a resistor, and then everything here will be replaced by 1 as well. But first off, I can work from the ground up. I'm going to replace this first MOSFET by a resistor. So I'm looking at the drain, and the rest is grounded. So I go back here. Where's the MOSFET? Okay, it's this situation. All right, I'm looking at the drain, but the source is grounded. It's not connected to RS. So here RS goes to 0. So this goes to 0. This goes to 0. I'm left with RO. And in our case, this is M1, so it's going to be RO1. Now, similarly, okay, we have a MOSFET that's connected here to RS, where RS in this case is RO1. So I'm looking at the drain with the source connected to a resistor. So this is the situation. All right, I got the drain, and RS is RO1 in our case. So we can use this equation, all right? These equations are equivalent for the PMOS and the NMOS, right? That's sometimes it happens, right? It's just equivalences in the electrical configurations. So I'm going to use this equation. So it's going to be GM1 RO1. No, actually, not GM1. It's going to be GM3 RO3 RO1. Yeah, GM3 RO3 RO1. Why GM3 RO3? That's because it's associated with this transistor. RO1 is RS from this one. So this is my RON. Now, R out is the resistance when I'm looking at the output. Now, you might see we have a resistive network here connected to ground, a resistive network here connected to ground, just like the previous lecture. This is in parallel. So we have R out equal RON parallel with ROP. This is the equation for ROP. This is the equation for RON. So this is my R out. Now, to find the gain is minus GM R out. The bro code said that the GM is equal to GM1, and the R out is equal to whatever we just calculated here. And that's how we found the gain, minus GM R out. So this is how you find the gain of a differential amplifier. So key takeaways from this video is understand the point of the differential amplifier, understand that it gets rid of the noise, look at the proof to convince yourself that it got rid of the noise, and actually, if you're like, I forget the device called, like if you want to measure the heart rate of someone, like in the hospital or something like that, you can't afford to have big noise, because your heart, the signal that it sends for you to detect, is so small that the noise might be bigger than the actual pulses from your heart. So you can't have an inaccurate device, because that would throw off readings, and then a lot of doctors, like, you need very, very precise measurement for the heart, because matters of life and death sometimes, you know what I mean? So having a differential amplifier, that's a very, very great application in that case, because it gets rid of that noise completely, and you can see your signal better. So again, I got distracted by the actual application here, but understand the point of the differential amplifier, understand the proof, and then understand the point of circuit splitting. Go watch it again to understand the point of the virtual ground. Try to solve circuits on your own to see where you can spot those virtual grounds, because it makes your analysis simpler. All right. And just rule of thumb, whenever you have a differential amplifier, there should be a way to circuit split that thing. So find that symmetry, and electrical symmetry, by the way, and then split your circuit. So with that being said, let me know if you guys want a current mirror video, but I don't think, I think you guys are way, way, like, very smart, and you wouldn't need that. So take care until next time.